Welcome to the session. In this video, we'll discuss about 0th law and its applications, first law and its applications, and the concept of enthalpy. So before going into this, you must know why it has got 0th law of thermodynamics. Initially, Joule has done some experiments and he has evaluated first law of thermodynamics first. Then the scientists thought that there must be another law which will be basic than first law, and then they have invented zeroth law of thermodynamics. That's why they have given the name as zeroth law of thermodynamics. Zeroth law of thermodynamics will completely depend on equilibrium states. Here, the statement is if a body A is thermally equilibrium with body B and also with body C, then the body B and C are in thermal equilibrium. Here you can see if A and B are thermal equilibrium and A and C are thermal equilibrium, then B and C will obviously be thermal equilibrium. And this is the zeroth law of thermodynamics. The application of zeroth law of thermodynamics is thermometry, which will deals with measurement of temperature. All thermometers comes under thermometry, which will use zeroth law for their application. For example, if you take an example of glass thermometer, mercury glass thermometer, where mercury will be in glass bulb, and when it is kept in a hot body, the heat will be transferred to the mercury so that it starts expanding. When it is expanding, it will move inside this tube, which will be having a calibrated scale to that. So it will expand until the temperature of the body is equal to the temperature of the mercury. That means until the mercury attains the same heat as the hot body. So here until it attains equilibrium state. So with that we will calibrate the temperature of the body. Likewise, there are many types of thermometers where we will calibrate the temperature of the body by when it attains the when the thermometer or the fluid in the thermometer attains the thermal equilibrium state with the hot body. Here, the changing property in the thermometer is called thermometric property. Here, there will be a change in length from which the change in temperature is calibrated in this glass thermometer. So here, the change in length is there. That's why length is thermometric property. Likewise, if you take constant volume thermometer, then there will be change in pressure. That's why that pressure, the change in pressure will be calibrated as change in temperature. That's why pressure is called thermometric property. Likewise, in constant pressure thermometers, there will be change in volume which will be calibrated as change in temperature. That's why volume is taken as thermometric properties. So this is the main application of zeroth law of thermodynamics. The next concept is first law of thermodynamics. For demonstrating the first law of thermodynamics or for evaluating the first law of thermodynamics, Joule has demonstrated an experiment in which he has sent he has converted heat energy into work and then he has reversed that as work into heat, and he has observed the relation between work and heat transfer. Here you can take he has taken a adiabatic cylinder in which there is some fluid, working fluid, and there is a stirrer which is connected by a pulley to the weight. And to calibrate the temperature change, he has given a thermometer inside this adiabatic wall. So adiabatic container is nothing but which will only allow heat transfer without any work transfer. So there will not be any, there will not be any heat transfer, only there will be work transfer in the adiabatic container. So by pulling this weight, this pulley will rotate. Because of this, this will rotate and these stirring pads will stir and create heat inside this fluid. And the increase in the heat is calibrated by using this thermometer. The temperature increase will be calibrated in this thermometer. Then he has noted how much work is converted into heat. Then he has reversed the same experiment and the work is again converted into heat and heat is again converted into work. Then he has drawn this graph from 1 to 2, from changing of from 1 to 2, the work given is W1 to 2. And while coming back 2 to 1, the heat transfer is Q2. So the cycle completed by a system with two energy interactions, that is work transfer followed by heat transfer. From that, he has given the law for first law of thermodynamics from the law of conservation of energy. The law of conservation of energy is nothing but energy can neither be created nor be destroyed, and it can only transform from one form to another form. So what he has observed is the work transfer between 1 and 2 is directly proportional to the heat transfer between 2 to 1. So the work done in the cycle must be equal to some constant into the work done throughout the heat transfer throughout the cycle. And that constant he has given as J, which is called Joule's constant. So cyclic integral dW is equal to J into cyclic integral dQ. Why cyclic integral is given to dW and dQ means because these are path functions which cannot be calculated by knowing only boundary conditions. For calculating work or heat transfer, you must know the path followed. That's why they has to be written as cyclic integrals. So this is the first law of thermodynamics undergoing a cycle where J is called Joule's constant and also mechanical equivalent of heat. That means if you take work and if you want to equate work and heat, there must be some equivalent and that is J, and that's why it is called mechanical equivalent of heat. Next, first law of thermodynamics undergoing a change of state in closed system. If a system undergoes a change of state during which both heat transfer and work transfer are involved, the net energy transfer will be stored within the system as it is named as internal energy. So if the heat supplied is Q and you are getting work done as W, Q minus W will be the change in internal energy of the body or the system, from which you can get Q is equal to the heat supplied to the system will be converted as work and remaining thing will be the change in internal energy. If there are many processes in this, like for example, you can take this one, the right one, where there are three heat transfers, that is Q1 is going out and Q2, Q3 coming in, and four work interactions with the surroundings, that is W1, W4 are going inside the system and W2, W3 are coming out of the system to the surroundings. Then the equation will be the heat transfer which is given to it will be positive and which is going out will be negative. That's why Q2 plus Q3 minus Q1 is equal to, and the work done which is done by the system is positive and on the system is negative. That's why W2 and W2 and W3 are positive and W1, W4 are negative. But the difference between these two will be the change in internal energy. There are many different forms of stored energy in which there is transitional kinetic energy, and you can see this rotational kinetic energy where energy will be half mv square, and vibrational energy where energy will be half kx square, and nuclear binding energy and electron energy, these will come from chemical energies. These all are minimum amount and these are the different forms of stored energies. So in a macroscopic approach, energy E is nothing but kinetic energy plus potential energy plus internal energy. U is internal energy and its units are joules. So in the absence of motion and gravity, the kinetic energy will be zero and the potential energy will be zero. So the energy will be equal to the internal energy. Then Q can be written as delta U plus W. In differential form, it can be written as dq is equal to dE plus dW. Here, d is inexact differential. So dq is equal to du plus dW, where dW can be the work done in many forms like PdV, shaft work, electrical work and all, in which PdV work is considered as the maximum work. That's why dq is equal to dE plus PdV or dq is equal to du plus PdV, where q is equal to delta E plus PdV or q is equal to delta U plus PdV, and this is the equation for first law of thermodynamics. Next concept is energy. Energy is a property of a system or capacity to do a work, and it is the property of system. Because the heat energy and work are path functions, they are not properties of system, but energy can be taken as property of system. For demonstrating that, you can consider the system which which is done between state 1 to 2. If it first initially while going 1 to 2, if it follows path A, then we can write the first law of thermodynamics equation as QA is equal to delta EA plus WA. And if it follows path B, then QB is equal to delta EB plus WB. We know from Joule, the first law of thermodynamics, the sum of work done in the cycle will be equal to the sum of heat transfer in the cycle. So WA plus WB is equal to QA plus QB, which can be written as QA minus WA is equal to WB minus QB. Because QA is given, heat is given and work is done. So the work done will be lesser than heat supplied in A. But coming to B, their work is done, then heat is evolved. So the work done will be higher. That's why WB minus QB. Then delta A is equal to minus delta EB. For suppose if the path follows the between 2 to 1 is C, then delta EA will be minus delta EC, which will clearly given delta EB is equal to delta EC. So the value of energy is not depending on the path followed by it. So it is not at all depending on the path followed by it. So it depends on the exact values of that. That's why they can be taken as point functions. That's why they are properties of the system. Next, energy of an isolated system. An isolated system is one in which there is no interaction of system with the surroundings. We already discussed about it. There will not be any interaction of energy or mass with the system and surroundings. Then that system is called isolated system. So for an isolated system, dq is equal to 0 and dw is equal to 0. That means E is equal to 0. That means E is constant. So the energy of an isolated system is always constant because there is no interaction between system and surroundings. The energy will stay in the system only. Next concept is perpetual motion machine of first kind, PMM1. There can be no machine which would continuously supply mechanical work without some other form of energy disappearing simultaneously. Such a friction machine is called as perpetual motion machine of first kind, PMM1. That means for any system to convert heat into work or work into heat, some amount of work will be taken for the running of the system. If in a case where the complete work can be converted into heat, and again if the heat can completely convert it into work, then that cycle will be continuous, which is not possible. And that type of machine is called perpetual motion machine or first kind. Same way, for any machine which will not consume some energy to do work, then that machine is PMM1, which is impossible.